All right, we're jumping into lesson 10.2 and 10.3. We're going to cover it all at once because they all deal with solving systems using substitution. So our very last lesson, we solved these systems using graphs. So if you put them on the graph, the one point where they cross would be the one solution to the answer. If they don't cross at all, then we found out there's no solution. Or if they are actually the same line, then there's an infinite number of solutions. Now, that's not the only way to solve these systems. There's a way we can find that ordered pair that works for both one of these equations algebraically, and that's what we're going to look at today. And so there's more than one way to do it algebraically. Today we're going to specifically look at substitution, where we take something and substitute in. So the big idea, substituting an expression that equals a single variable is an effective first step for solving some systems. And then the second big idea from 10.3, substitution is a reasonable method to solve systems whenever you can easily solve for one variable in an equation. So there's times where one of them may not even be in one of these perfect forms like y equals or x equals, but you can rearrange it pretty quickly to get it in that form. And then substitution would be a good method at that point. So this should seem familiar. You definitely covered this in Math 8 at one point. Okay, so what we're going to look at here is how do we solve these without putting it on a graph, although you could. How do we find the x and the y value that not only works for the first equation, but works for the entire system? So if you plugged it into both equations, they're both going to come out true. So just imagine for a second, I told you that x equals 10 and y equals 2, and I said substitute them. I used that word. Think about what you would do. You would say, oh, if x equals 10, then I can change 10 or substitute 10 in for x. And if y equals 2, I can plug that in for y. That's called substitution. Now, we're not actually going to use those numbers, but it's the same idea. Now, when we substitute, it's not going to be a single number that we plug in. It's going to be actually an algebraic expression, and I'll show you what I mean in a second. But it's the same thing. If you know what y equals, if I told you y equals 10, you can change y to 10. Well, actually, I already know what y equals in this first one if you look at it. Y doesn't equal a single number. Y equals all of this. Y also equals all of this. So two ways to think about it. First of all, if y equals both of these, then that means they equal each other. So you can write it that way. You can say 7x plus 25 equals negative 5x minus 11. We can start by doing it that way. Or we can say, well, I know y equals this whole thing. And if that's what y equals, just like if y equals 10, I can come over here and make it a 10. If y equals 7x plus 25, I can literally come over here and substitute that in. So I'm going to change y to what it's equal to. Not 10, but 7x plus 25. So I'm actually going to rewrite this equation, but I'm going to change y to what it's equal to. Again, if it was 10, I don't think anyone would have a problem changing it to a 10. Now y doesn't equal a single number. It's this whole expression, 7x plus 25. So we're going to put that in. So rewriting this whole line, but changing y to what it's equal to, 7x plus 25 equals negative 5x minus 11. And now we have an equation that you've been spending years learning how to solve. So we should feel pretty good about this. So let's go ahead and solve it. You've got an x on both sides of the equation. That's going to happen a lot here. Remember that we want to eliminate one of them so that there's only one variable left, either on the left or the right. It doesn't matter. Ideally, you do want to go after the smaller of the two coefficients. When you do that, you keep your numbers positive, and we make less mistakes that way. But you technically can get rid of either one. You could minus 7x from both sides and get rid of it, and that would work. Or you could add 5x to get rid of the negative 5, and it would work. Ideally, again, we want to make positives. So the smaller of these two coefficients is the negative 5 because it's negative. And so I'm going to get rid of that one. Now notice how I lined it up perfectly underneath whatever it's going to interact with. So it's going to cancel here, leaving me negative 11. Add these together. It's 12x. And now we've created a very simple equation that we can just run and solve here. So we're going to minus 25. 12x equals negative 36. Then we're going to get negative 3. Now you may think we're done. You might say, well, the answer is negative 3. But think about what we're solving. Think about when we had those graphs. When you solve the system, you were finding a pair of values that make this true. So the x and the y. So just plugging in -3 doesn't make anything true here. We need a y value to make that true. So all of this work helps you find what x equals. Sometimes it's going to be the opposite. You'll find out what y equals. But regardless, once you have one of these variables, you're going to go back to either one of the equations, and it doesn't matter. You're going to go back to either one of them, and you're going to plug in your value or substitute it. -3 is going to get put into this one for x, because that's what it is, or this one for x. And it will produce the y that we need. So here's what I mean. I'm going to go back to the first one. It doesn't matter. It doesn't have a negative, so I'd rather work with this one. And again, you could have chose this one. And so I'm going to plug in -3 or substitute -3 in for x. So 7, x becomes -3. So that's -21. And -21 plus 25 gives me a final answer of y equals 4. And so I have now solved the system. I have found the ordered pair. And so there's one solution. And we always list it as a pair, like if it was on a graph, x comma y, so -3 comma 4. And so if we graph these two lines, this is the point where they would cross. We have just found it algebraically, a little bit different. So what I want you to do is I want you to try the next one, pause the video and try it and see how you do, and then follow along. Okay, so if y equals this, that means I can substitute it in here. So I'm literally just going to take this and plug it into this. So I'm rewriting this one, but changing these two things out. That's what y equals, so I can change it. So 3x minus 4 drops in for the y, and it's going to equal 5x minus 10. Another way to think about it is if y equals this and y also equals this, then they have to equal each other, so we can just write that they equal each other. Just another way to think about it. Now let's solve it. We have an x on both sides. We got to eliminate one of them. You technically can do either one and still get it right, but ideally we do want to get rid of the smaller of the two, so I'm going to minus 3x. So it goes away. This is -4. So I have 2x minus 10. Nice and easy from here. Get that x by itself, so add 10. And so I get 6 equals 2x. X equals 3. So over here I got x equals -3. And over here I got +3. Now again, you're not done until you have an ordered pair. So I need to go back to one of these. It doesn't matter which one, so I'm going to go back to the first one for no specific reason. And I'm going to plug in or substitute in the number I know that x is equal to. So I know x is equal to 3. I'm going to plug that in for x. So I get y equals 9 minus 4, so y equals 5. And now I box those in. You don't need to really because they're not your answer. Your answer is the fact that you have one solution, and that solution is 3, 5. Okay, in the next video, we're going to look at ones where the x is isolated, and we're going to plug in for x instead of y.